Imagine that you're looking at light coming from a bulb. The individual photons can be thought of as waves. If we look at the light from the bulb coming towards us, then we see the photons end on, and we can draw the vibration of the wave as a double-headed arrow, showing its maximum and minimum amplitude. Now, there's not just one photon coming from the light bulb. There are millions and billions of them. But they're not going to be moving in the same way. They're all going to be moving at different planes of vibration. And we can draw that like this. Each wave, each single photon, has a different plane of vibration. To help us to understand polarization, imagine that we want to post some letters in a postbox. In order to do so, you have to have the letters lined up in a slot. That's something you learn when you're very little, that if you try and post the letter end on, it doesn't go in the postbox. We have to have them horizontal. And if we were to be able to sit inside the postbox and look at the letters which are coming through, then we can see that they're all coming through in the same direction. And that's a little like polarizing light. The easiest way to polarize light is to use a Polaroid filter. This is a filter which only allows light of one particular vibration to come through in a single direction. We call light that has only got one plane of vibration polarized light. So if we look at our light coming from the light bulb and the Polaroid, then what comes through is polarized light, light with its plane of vibration in only a single direction. The polarizing filter has a polarization axis, and we show that by the arrow on the diagram. And it's light which vibrates in that plane which will pass through. Okay? Now, if I use my polarizing filters, what you'll see, is that as I rotate the filters, the amount of light that gets through decreases. There's less light depending on the plane of the polarizers. Now, we need to think about why that is the case. When the two polarization axes are parallel, there's very little diminution of light. Quite a lot of the light gets through. However, when the polarizations are perpendicular, then no light will get through. And if we were to draw a diagram to show that, that's what it would look like. Okay? So you need to be able to explain in an exam why it is that crossed polarizers stop light getting through. Now, we can also polarize light not only by using Polaroids, but by reflecting it off a non-metallic surface. So if we have light with its plane of polarization in all different directions, it then reflects. What we find is that the reflected light will be polarized in a direction parallel to the surface, which can result in what's known as glare. And that's why Polaroid sunglasses are used to reduce the glare. Glasses with polarizing filters are useful in sports such as boating, fishing, where the glare from the water can obscure the view of obstacles or fish. And they're also used at skiing or on the beach sometimes. So polarization is a very useful physical fact. Now, polarization can also occur when light is scattered or refracted. Okay. Now, polarization actually tells us something about the nature of light, because something that we know about is that only transverse waves can be polarized, which tells us that light must be a transverse wave. Longitudinal waves cannot be polarized. So if we have a wave and we can't polarize it, then we know that it's longitudinal. And in some ways you can think of that because the longitudinal wave is already polarized. The wave direction, the direction of wave travel and the plane of polarization are already in the same direction.